Let us say an object was kept on a horizontal surface. So this is the object that was essentially kept normally on a horizontal surface with the entire base of the object in contact with the surface. Now let us say we are applying a force F at a certain height from the ground. Let us say this force F is applied. Alright. So naturally the object will tend to tilt. Okay. Let us say the object does not topple, meaning the force F and the torque that it generates, let us say, is not enough to completely topple the object about this point. Meaning, as per our previous analysis, mg into b by 2. Let us say this is the force of gravity mg into b by 2. This happens to be the perpendicular distance. Mg into b by 2 is greater than F into h. So this is the force F and this is the perpendicular height h. Let us say that means Fh is less than mg b by 2. Now even in such a situation, even in this particular case, there is going to be shift of normal reaction. So what do I mean by that? Meaning the normal reaction that was earlier being applied from the center of mass, and that normal reaction was essentially opposing mg. So this is the normal reaction that was being applied from the center of mass, and it was opposing mg in the initial case when the block was kept flat with entire base in contact with the horizontal ground. This normal reaction is now going to shift. There is going to be shift of normal reaction. The normal reaction will shift over here and will be applied now via the edge point, or it will, let us say the entire bottom surface of the block is still in contact with the ground, then the normal reaction will be applied through a point that is towards the right of the center of mass as seen in this diagram. So the normal reaction is essentially going to shift from being applied via the central point to being applied from a point that is towards the right hand side. If let us say the entire bottom surface is lifted apart from the rightmost point, then this normal reaction will have to be applied through the rightmost point only. So this is an important realization, that normal reaction is shifting as the force F is trying to topple this particular object. Now let us say the force F is just sufficient to topple the object. Then at the critical instant of toppling, the center of mass, now this is a very important observation, the center of mass of the object is going to be directly above the point of contact. So what do I mean by that? So as the object is just toppling and falling down, this is the point of contact and this is the line that goes directly above the point of contact. So the center of mass of the object is going to lie on this particular line. That is what we mean. During the instant of toppling, the center of mass will be above the critical point, or the center of mass will be above the point of toppling basically. So this is an important observation, that center of mass happens to be above the critical point. I'll write it down over here. Center of mass is above the critical point. Okay, at the instant of toppling. So when does this happen? At the instant of toppling. At the toppling instant. This is something very important to understand. Now based upon this phenomena, we can analyze the situation that has been shown over here. In the first case, in this particular diagram, let us say this is case 1. In this particular diagram, we clearly see that this is the center of mass, okay, of this object with a circular cross section. It could be anything. It is just an object with a circular cross section. So this center of mass is towards the left of the critical point. So there is a normal wedge with angle theta and there is an obstacle in between. So this is the obstacle. Alright. So this center of mass is towards the left. So gravity will be acting like this and normal reaction at the critical point will be acting like this. If you can visualize the torque that these two forces will provide, the torque will be in such a counterclockwise direction. And hence no toppling will happen and this object will not be able to topple over this critical point. Alright. Now, in the second case, we can see that the center of mass is just above the critical point. Let us say this is the center of mass and this center of mass happens to be just above the critical point, exactly above the critical point. The center of mass is, let us say. Alright. So let me draw the center of mass. Yeah. It is just above the critical point. What does this mean? This means that this object is in something called as unstable equilibrium, and let us say even if small amount of push is given, let us say somebody blows air also, let us say, and even an infinitesimally small amount of push is given in this direction, then this object will topple like this. Okay. In some questions we can also find out, like this height has been asked, let us say this height is asked, what should be the height of the obstacle such that the object just topples from over it. Then this height is the same as this height and this also happens to be the radius. Now if this angle is theta, then we should be familiar with theta giri, as I call it. This angle also happens to be theta, this angle. Alright, and then this angle is also theta. So essentially now things are very simple for us, because if we do extend this particular line over here, then we can see that in this triangle, this particular distance, this distance is going to be r cos theta, and then the height will be r minus r cos theta, because this entire thing is r. So this distance happens to be r cos theta. This entire thing is r. So this particular height will be r minus r cos theta naturally. So this is the critical height at which the object will just topple. So height is going to be equal to r minus r cos theta. Also can write it down as r into bracket 1 minus cos theta. Alright, now let us look at the third example. Here the point of contact is over here and the center of mass would be over here. So we can see that clearly this object is going to definitely topple without any external push, or even an infinitesimally small push will not be required for this object to topple, because this is the vertical line from the point of contact and this is the line from the center of mass along which the gravity is acting. So if we can see now, if we can analyze, it is very simple to understand that normal reaction is acting upwards and gravity is acting downwards. So the combination of normal reaction and gravity is going to produce a clockwise torque, and there is nothing to stop this clockwise torque, and hence this object is definitely going to topple even if it is kept at rest. This particular small wedge or small obstacle of height h is not going to be sufficient in order to make this object topple. So herein we can say that since the radius of the object is large, this angle theta remains as it is, since the radius angle theta is the same in all the three cases. Since the radius of the object is large, we can say that here h is going to be less than the critical value, which is r 1 minus cos theta, because r is large. Let us say this is the third case, this is the second case, and this is the first case. Alright, So we can say here R in case 3 will follow this relation, R in case 2 will follow this relation, and in case 1 we can say that H is greater than R1 1 minus cos theta. So because of that, in case 1 no toppling will happen, and in case 3 definitely toppling will happen, and in case 2 it is at a critical condition wherein it is just barely stable. Even a slight amount of push, an infinitesimally small amount of push, will also make it topple. Now we can further analyze many such situations and many such objects. Okay, in all such scenarios it is assumed that the friction is sufficient enough to provide enough amount of restrictive force, or rather opposition because of friction, that no sliding is happening, otherwise sliding analysis will be separate. So here we want to do only toppling analysis. So here all the angles are theta. Now it is very easy to figure out what is going to happen. Let us say in critical case the center of mass will be exactly above the toppling point. This is the learning that we have from previous analysis. So this would be the critical case. For this guy, the critical case would be similar. Center of mass is above the point or line of toppling, basically. For this guy, let us say it's a n-sided polygon. To be exact, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10-sided polygon is there. So to be exact, let us say this is the center. Then in that case, the toppling point is going to be this particular point. Alright, like so. So geometrically speaking, the student can analyze this particular all these situations to find out the relation between the sides, etc. Like for example, I'll give you one example and leave the others for your imagination and pursuit. So this is, let us say, h by 2. This happens to be r, the base radius of the cylinder that has been kept. So this happens to be h by 2. This happens to be r. Alright. Now you have to geometrically figure out, according to theta giri, that this angle is going to be theta. Why? Because this angle would have been theta, and if I extend this, then that happens to be the corresponding angle of parallel lines. So if I draw this line, that angle simply is the corresponding angle of parallel lines. So it is understood that that angle is going to be theta. Alright. So we can now write down tan theta as r divided by h by 2. Here we can write down tan theta to be equal to r divided by h upon 2. That's it. Therefore, theta is going to be equal to tan inverse of 2r upon h. All of us while studying physics should be familiar with the inverse trigonometric functions, definitely. So similarly, other objects can be analyzed. So this is the critical condition. Critical condition meaning condition for the object to be just able to topple, basically. And what is the critical condition? Center of mass. I am writing it down over here. Critical condition is center of mass above the critical point or the toppling point. So this is the condition always.